In this video we'll discuss circular motion. Before we do that, I just want to make sure everyone's aware of angles in radians. And what do I mean by a radian? Well, a radian is defined as the angle swept out at the centre of a circle when the arc length is equal to the radius. So if the arc length was S and the radius was R, so this arc length swept out through that angle. If S equals R, if we compare S to R as a ratio to get the angle, we will find that that angle is equal to 1 radian when S equals R. Okay, so that angle in radians is 1 radian when S equals R. If you imagine going all the way around the circle 360 degrees, well, using this, S would be 2 pi r. That's the circumference of the circle. And if I divide by r, I get 2 pi radians. So 360 degrees, which the degree is just a number that has many factors, so you can half your circle, a third, a quarter, divide by 10, 72. Many numbers can go into 360, which makes it a good number to split your circle up into. But in radians, 360 degrees equals 2 pi radians. If we went halfway around the circle, so if we just went half the way around, 180 degrees, that would be pi radians. A 90 degree angle would be pi over 2 radians. And actually, if you want to make the link between what 1 radian is in degrees, if I divide both sides of this equation by 2 pi, so for 1 radian, which you can write as rads for shorthand, 1 radian is equal to 360 degrees divided by 2 pi, which comes out as about 57.3 degrees. Okay, so just bear in mind, circular motion, whenever we talk about angles, we mean in radians. And that's what 1 radian is. Okay then, circular motion. So here's a circle, radius r, here's an object. If this object is going to move around this circular path, if we say that it's moving with linear velocity v, as it moves around the circle, it's traveling this direction, it moves around the circle, traveling this direction, goes further around. So at any point in the circle, if its velocity, the magnitude of its velocity, so if the speed is constant, so the size of the velocity vector is constant, we call this uniform circular motion. However, obviously velocity is a vector quantity, so it is changing direction, so it is actually changing velocity, it is accelerating. Okay, so in circular motion there is an acceleration that we'll discuss later. Something else to discuss is the fact that if we think about something spinning on a rotating disc, depending on how far out the object is, so let's just say the object's at this position or maybe this position, if you think about the path it takes, so the object closer to the center doesn't travel as far as the object further away from the center. However, if this disc is spinning, then both objects should move through one complete revolution in the same time. But because this one's not covering as much distance, that must actually be traveling slower around the circle than the object further from the center. The key thing is now, we can't just talk about the linear velocity without thinking about the angle at which the object rotates around. So this is something called angular velocity. So not only do we have a linear velocity, at any point in its journey we can take its velocity to be in the direction tangential to the motion, but we can also think about the rate at which it's sweeping through a certain angle, given by the angular velocity. So let's think about linear velocity. That would mean how far around it's gone in a given time. And as a special case, we could say to complete one revolution, it will cover the circumference of our circle, 2 pi r, and that would be in a time which we'll denote as the time period, the time taken for one revolution. And if you realise that the frequency, how often, how many rotations per second, is linked to the time period by this little equation, f equals 1 over t. Well, we've got 1 over t here, so we can actually replace that if we know the frequency of rotation with that. Now the angular velocity is slightly different to the linear, meaning the distance travelled. The angular velocity is actually the angle which the disk will sweep through in a given time. And likewise for the special case of going round once, if you went round once, well, we've just discussed the fact that that would be 2 pi radians angle, and then the time taken would be the time period. And likewise we could replace 1 over t with f to get 2 pi f. And then the only other thing to notice is that there is a link between linear velocity and angular velocity. If I just kind of separate this term out here, 2 pi over t is the angular velocity, so v is equal to omega r. And there's the link. It doesn't matter what rate of angle you sweep through, the further you go out, so the greater the radius, the greater the linear velocity. Okay, so this one would be travelling slower than this one because it doesn't have to cover as much distance in the same time. Okay, so if there is a change in direction, so there's a change in velocity, then there must be an acceleration, and we can define or derive that acceleration by looking at this. So let's say the object's here, and there's the linear velocity, and then it gets to this position. Okay, and it's still travelling with the same magnitude, but so the speed's the same, but it's changed its direction, and in doing so it's swept through this angle theta, and it's actually covered this arc length s. We can look at the velocity vectors to work out the change in velocity. So if it was travelling with a velocity vector initially here, and then after a given time it's now, this is the velocity vector. Okay, so the v and v. To go from this vector to this vector, that has been the change. Okay, so it's gone from this vector, there's been a change in velocity, and it's now, this is the new velocity. Okay, and likewise, if you look physically at the triangle of radius r, and let me just draw a straight line there. Although we are saying it's going to cover that arc length, if you think about working out an instantaneous acceleration, at a very small period of time, that won't have gone through much of an angle, and actually the arc length will be very, very similar to this length. Okay, so actually I'm drawing out this triangle of lengths r, angle theta, and displacement s. Now this angle here, that is that angle, because if you think the velocity, which is 90 degrees, and the velocity here is 90 degrees, so tangential to the path, if we swept through that angle, well, if they're just 90 degrees to that, and they're going to move through the same angle to go from this position to this position. So what we've got is two similar triangles. In fact, let me just draw these much clearer. So we've got two similar triangles, each have angle r, theta, and this went from this velocity to this velocity because of a change in velocity, and this is radius r, and displacement s. If we suggest that the velocity is the displacement over time, if we rearrange that, we can say that that must be the velocity times the time taken to move that distance. And because these are similar, what we can say is that if we do this over this to give the angle, so the delta v over v should be equal to the angle, but that angle is also equivalent to s over r, which is v t over r. If I multiply up by v and I divide by t, I get change in velocity over time is equal to v squared over r. And change in velocity over time is acceleration. So the acceleration, or more to the point what's known as the centripetal acceleration, is equal to the linear velocity squared divided by the radius of the circle that the object's moving through. Now, what we can also suggest then is if something's going to accelerate, there must be a resultant force, and the resultant force must act in the direction of the acceleration. And thinking about Newton's second law, F equals ma, we're simply saying that the centripetal force is equal to the mass times the centripetal acceleration, and that is mv squared over r. Now earlier on we said there was a link between v and omega, so you can actually put all this in terms of omega. So if I replace v here with this term omega r, if I square v, I then get omega squared r squared divided by the radius r, and then one of the radius cancel to give omega squared r. So actually the centripetal acceleration can be v squared over r, or it can also be in terms of angular velocity omega squared over r. Okay, so I'll leave this video here. I'll move on to another video that will just quickly summarize the equations we've looked at, and then it'll talk about some examples of circular motion, uniform circular motion, and then I'll make a third video that will look at going through some exam style questions.